So thank you very much for this nice introduction. For me it's really a pleasure and great honor to return after such a long time, almost 15-20 years, to my alma mater. During the last 7 years I was working at the Technical University of Vienna, when I got to know at least from my perspective, really amazing numerical methods, which I want to talk about. And I hope you find them also interesting and possibly useful in your research. So I usually in my research do something else. I work with the plastic collapse of structures, so not exactly with these two methods, but some of the second one at least I use a lot. So in this talk I am going to speak about two different topics. The first one is hyperdual numbers, which is a structure which allows us to calculate numerically the first order and second order derivatives with no truncation error, which is amazing. So we will speak about this topic about 15 minutes, and there will be short discussion, and then we go to the second topic, which is the deterministic optimization and the branch and bound method in particular, which is the method which allows us to calculate the global minimum in the non-convex optimization with certainty, which I found also pretty interesting. So let's go to the first topic, which is the hyperdual numbers. So the problem which we want to solve are the numerical calculation of derivatives. So during our outline we will speak shortly where we need numerical derivatives, and then I will show you the three methods which can be used for their calculation. This is the standard finite differences, then the complex step method, and hyperdual numbers. And I will compare, I programmed all of these three methods, so I will show you all of these three methods at one numerical example, and you will see the differences and advantages of each. So we can start with where do we need numerical derivatives. So I just gave you two examples. So first one is, for example, when you deal with the nonlinear finite element method, then you obtain the set of nonlinear equations, nonlinear algebraic equations, and these you have to solve by Newton method, for example, and in this way you need the gradient matrix or stiffness matrix. Of course, in many cases you have an analytical expression for the stiffness matrix, but not in all cases. For example, in some complicated problems with friction, there is a problem to get these analytical formulae, but even if you get them, and I wrote them only two examples, just the first is the stiffness matrix for the small strain plasticity, and these three rows is a stiffness matrix for the case of hyperelasticity for the moon-riveting material. So we see that also in the case when you have these formulae, they are not so easy, so you can make mistake in derivation of this formulae, or you can make mistake in implementing this formulae. So it's always good to have some method by which you can check if your implementation of the stiffness matrix is really the tangent matrix, and you can do it through numerical derivatives. And the second problem which came to my mind was optimization problems, because if you do some kind of optimization and you solve it, for example, with the quasi-Newton method, you need to numerically or need to evaluate the first order approximation of Hessian, and if you even use the Newton's method for minimization, you need a full Hessian, so second order derivatives. So there is a need of second and first and second order derivatives as well. So let's go to the first of the three methods. This is a standard finite differences. So the finite differences formula are easily derived using the Taylor expansion. So if you have a Taylor series, you truncate the high order terms at point x, where you want to evaluate the derivatives. After truncation you rearrange the formula and you get directly. This is the formula for the first order derivatives and for the second order derivatives. And you see that you have the truncation error, but also round-off error. And now we look to the numerical example, which is this function at this point. And we look to this in the logarithmic scale. So the small values of h are on the right hand side. So if you look to the first derivative, we see that at the beginning the error is high, but it decreases with the smaller values of h. But then suddenly the error starts to grow because of the round-off error, which goes to infinity. And the reason for this unpleasant behavior is the subtraction in the numerator. So where we have minus here and here as well. And we subtract the two values with a very similar value. So this causes this problem. So in order to use this formulae, it would be good to use this minimum. However, this is not so easy to find this minimum numerically. And even if you find a stable way how to find this minimum numerically, then even the value of this error here can be too high for your purposes. And for the second order derivatives, it's even worse. This is this dash line. Now let's go to the complex step method. The complex step method is based on a very clever idea. So you again make the Taylor expansion at the point x where you want to evaluate derivatives, and you make a step in a component, I component, where it's interesting for you, which you want to evaluate in the imaginary direction. So h times imaginary unit times EA. And then you proceed the standard Taylor series, and you see that on the right hand side every odd term is real and every even term is imaginary. So if you do truncation and then you do imaginary projection on this equation, you immediately get the formula for the first order derivative. And presently that you can see that there is no subtraction in the numerator. So it seems that this formula will not have problems with round-off errors. And numerical research supports this idea. So the first order derivative using the complex step method is by the green line. So at the beginning it's high, it goes down with the smaller values of h, and then the relative error stays at the lowest possible limit, which is the 10 to the power of minus 16, which is the basic round-off error for double precision. So it's amazing, it works well. If we do the real projection of the same equation, we can get in the same way the formula for the second derivative, which is here. But this formula has unfortunately the minus here, so it seems not to work, and it really doesn't work. So this is the green dash line, and we see that it works as bad as the final difference formula. Now let's go to the hyperbola numbers. Hyperbola numbers is a special structure. The idea behind hyperbola numbers is the following, that we want to make the same trick as in the complex step method, and we want to make a imaginary step from the point x where we want to calculate derivatives, but not in the complex numbers, but we want to do it in some other space. And Jeffrey Fike, who invented this method in year 2008, so it's pretty new, invented this structure. So hyperbola number is a quadruple, so 4 real numbers. We have one real component x1 and 3 imaginary components with imaginary units epsilon1, epsilon2, and the multiplication of these two imaginary units serves as a third independent component, epsilon1, epsilon2. We have some rules, so epsilon1 squared, epsilon2 squared, and these combinations are 0. So we have 4 components as in the case of quaternions, but this is of course different structure. Now what is different, for example, that the multiplication is commutative. So now we want to look how we can calculate the basic operators. So plus and minus, so additional subtraction is very easy, so it equals to the addition of the subtraction of each component. If you make multiplication, so by using the standard rules, we get this explicit expression for multiplication. Then if we want to evaluate the inversion 1 over a, we can evaluate it from this equation. So this is a, this is 1 over a expressed as a general hyperdual number. And if we multiply these two brackets and compare components, we get this explicit form. Now, and if we multiply this by b using this rule, then we get explicit form for the division, which can be used for any values for which a1 is non-zero. So this is the basic operators. Interestingly, hyperdual numbers have commutative multiplication, so not like quaternions, but this is not a field like a complex numbers. And the problem is that there's this division or this inversion element doesn't exist for all x which is non-zero. So, for example, for element which has 0, 1, 1, 1, we have no inverse element, so therefore it's not a field. Now let's go to the most interesting slide in this section, Taylor series. So we try to do the same what we did in the finite differences on the complex step method. We do the standard Taylor expansion. So we are again in multiple dimensions. Point x is the point where we want to evaluate derivatives. We make a hyperdual step, h times epsilon 1 at component I, which is interesting for us, and h times epsilon 2 on component j, and all other components here are 0. And if we evaluate the function at this point, we have a real number, which is the evaluation at point x, then the step times gradient, and the second order term. And now, interestingly, if we look at the cubic term and all other high order terms, they are identically 0 because they contain either epsilon 1 squared or epsilon 2 squared or epsilon 1 epsilon 2 squared. Even from the quadratic term here, the only term which remains non-zero is this one, h1, and the mixed derivative with respect to xi, xj. So from here we have 4 non-zero components, h squared times epsilon 1 squared, this is 0, epsilon squared times epsilon 2 squared, this is also 0, and only the mixed term is non-zero. From this term we have this, and from here we have 2 non-zero components, which are then here. So this is the nice that we have, that the Taylor exponential is finite, so we have no truncation. And now again, it's the same trick, we do the projection of this equation, so f equals to this. So if we make epsilon 1 projection, we immediately and divide by h, we immediately get this formula for the first derivative. And if we make epsilon 1, epsilon 2 projection, we immediately get this formula for the second order derivatives. And now we see that there is again no minus here, so we can hope that we will not have problems with round of errors. And really the results are really amazing. So we have the results for the blue lines. So we see that for small step stage, we have only the basic error 10 to the power 16, no truncation error. For the first derivatives and for the second derivatives as well. But not even that. If you look to the high values of h, we have also 0 error, which is just nice. Now there is something that remains, something which needs to be explained. So in order to use right in here, in order to use hyperdual numbers, we have to take our function, our real function, and we have to enlarge its definition to hyperdual numbers. In the complex step method, it is standardly done, but now we have to think about how we can enlarge the definition of any function to hyperdual numbers. So we already know how to make plus, minus, multiply, and divide, division. And for the evaluation of standard formula or standard functions, we can use a Taylor series. So now we rewrite again the Taylor formula at point x. Now at this step, so we have also non-zero component in epsilon 1, epsilon 2. And if you make the Taylor expansion again, we get this formula. So we have the linear terms here, here, and here, and the only quadratic term. And now if we set for the function f, which is arbitrary, for example, sinus, cosinus, or exponential, power, then we get the explicit formula, which can be used that here we can put hyperreal number, and here we get hyperreal expression, or enlargement of the definition of standard functions. So this is how it is used. If you look to implementations, for example, the new programming languages like Julia have standard implementation of hyperreal numbers. There are some libraries, for example, in Rust programming language. But this is so easy that you can program it in any language in a couple of hours, so this is not a problem. It works amazing. Of course, it costs anything. It costs something. So, for example, the hyperreal addition costs 4 real additions. Hyperreal multiplication costs 9 real multiplication and 5 additions. So it costs something, but it's worth it. And here there are some references. This is the first reference which I found from the year 2008. So let us conclude. The hyperreal numbers is a numerical vehicle which allows us to calculate numerically exactly derivative of the first and second order. And small notice, it can be enlarged to some. There are some different spaces which allows to calculate it in the same manner, for example, third order derivatives. But then you need a little bit different space than hyperreal numbers, but it's possible. So thank you very much. This is the end of the first part. Do you have any questions or comments?
So can you compare the speed of the finite differences, this method, and automatic differentiation? So did you test it or not? Finite differences and this, for example?
Yes. I program all of the diagrams. I program myself.
No, and you write this theoretical that it corresponds
No,
from.
I haven't compared the speed by myself. So if it's compared with analytical differentiation, it's an interesting question. It depends also on the implementation of the analytical derivation. Could be compared.
So is it better than automatic differentiation? Because we are using feelings here, and because it is as good as this, maybe even better.
For large program, this cost of one multiplication being 9 real multiplication is pretty big cost for 1 million unknowns if you want to compute the derivative of function. So you get 9 times more CPU time.
That's a question. It's interesting.
Finite differences, it's also costly. So
Yes, it is, and not so accurate, but still it's less than this.
yes,
The accuracy is not.
let's say twice or
Yes.
I think this
Twice.
this increase is linear, so or
It's linear,
so it is not as bad.
Okay.
I also think it's not so big deal because, according to my experience in finite elements, the assembling takes always the less time than solving the problem.
Depends on the complexity of the problem.
Depends on the complexity.
No, because it is different if it does the assembly for, let's say, 3 seconds or 27 seconds. This is
Of course. This is an interesting question to compare the automatic derivation and this.
and now you tested it just on these simple scalar functions, and you are differentiating just the scalar functions, or did you use it already in finite numbers?
No, I haven't needed it, so
Okay.
I used it only on this example. But there is an article, don't know if it's this one, but I can give you article where these hyperreal numbers are used in the fluid calculation.
Mhm.
I think on compressor Navier-Stokes or something. So there are such a tests.
You mentioned something about this. You are able to calculate any second derivatives, yes? So for any I, any j.
Yes, you can.
Because
Yeah,
somehow when you talk
This
about
is
it,
this is
seems
general
to me-
formula.
Yeah.
So here, so you choose, for example, the I derivative by the way where you put this increment on which component.
But you need to define all the functions for this thing. So not just sinus, cosine, exponent, and the polynomial, but for example, if we have something more difficult, we have, for example, 3 times 3 matrix, and we want to do logarithm of this matrix and take the derivative. And this would be difficult. I would need to define again also the matrix logarithm for this.
But I think it's possible. I have a presentation from Jeffrey Fike, and there are some matrix evaluations of again values of big matrices. So yeah, I think it's possible. But maybe we can try it in some example this compared with terms of speed. I think it's interesting.
Another point that I want to emphasize was that maybe it cannot be used in the calculations, but it can be used just to verify that your code is somehow working properly.
Also, I think yeah.
So I would again bring it to the place.
No, because we have problem with the time of the assembly. But we are using automatic differentiation, also with the Fike, and it's extremely slow.
And how much time does it take in comparison with the inversion of the matrix?
The problem is big, so it is nothing, but but still, because I was using XFAN during my postdoc, so this is finite element code written by Joži Korec from Lublin, and it is 6 times faster than Fike. And both is using automatic differentiation, but Fike is 6 times slower. And this seems that maybe this is implementable in everything. This is
It's
good.
implementable in everything. So I think it's a nice idea for testing.
What I find very interesting is that it should work even if your step size is quite large. So it seems yes it's variant.
It's weird, yeah. I think I also was also surprised by this.
Yeah.
This is because there is no truncation. There is no error in the Taylor expansion. This is perfect. You know, there is no
So
error.
So it could work really fast if you do not need use such small step size. So you can it could work faster.
Maybe what happens if you apply it to some not smooth function like absolute value and ask for a second derivative of that? Okay, no, I mean, so if you do finite differences, first derivative, you get some like regularization of the function.
I would expect something like this.
But which depends on the age. So
But
the
it
age
also
will
depends
how
on
much you
the
regularize it.
which formula one uses, because this formula cannot be used. So, but it's also an interesting question. So what does it do?
No differentiation.
No, but
This is not related to it.
so finite differences will give you something.
So you need to regularize it before. Yes.
No, but I think I would expect the same behavior. If the finite difference regularizes, why this is the same principle. It also comes from the Taylor
Okay, and
series.
this
So I would expect-
regularization will depend on the age. So here it looks like this. The hyperdual numbers are independent of the age. You can choose any.
That's
for Swiss functions. For non-Swiss functions should be also possibly, I haven't checked it, but possibly there are some articles.
Because this function is moved, we have.
But if you'd like to answer one is in the Julia package, in the environment, and for instance, there's this code by Jürgen Fuhrmann, so full fair and volume code where it's implemented is for comparison of parabola equations and advection equations, for instance. But how it's implemented in Julia, they defined all the basic functions like sine, cosine, exponential, and so on, using also hyper dual numbers. So whenever you write a function which is some composition of these functions, and you say, okay, use dual numbers, then fine, it automatically differentiates everything. But I suppose it doesn't have absolutely implemented. So maybe so that we implement this an extra function so that it can be composed with all the others.
Okay, so also take care of it before.
I suppose so. But I haven't tried that. That's usually for smooth functions. But in Julia and Bruno, so for the comparison with other codes, Bruno final volume method is a package which is ready to use. It's been implemented there, and for Julia it's just a matter of importing the package, basically.
I am not sure whether you said it, but or you said it 2 months ago. But if you want to calculate higher derivative, it's also possible. Yeah. So that essentially you need to there is also some
third
structure.
order, for example.
Yes.
Yeah, I mentioned it. Yeah. There are articles about the third order. If you need them, there are some, but you cannot use hyperdual number, but a little bit different structure, which is just made that the Taylor series truncates just after the next term. So I think by this you can find any formula for any derivative if you really need it.
Maybe it a little bit reminds, if you look at this algorithmic differentiations implementation, one of the methods looks very similar, that you redefine all the operations by some additional operation on some auxiliary numbers, and at the end of the calculation you have some derivative.
Real one.
Real one, yes.
Yeah.
So maybe it is in fact somehow connected with these operations on the hyperdual numbers. I don't know, but it reminds me a little bit.
And what does it remind you?
This, like this algorithm,
Yeah.
this hyperdual number, it reminds me the algorithm how one way of algorithmic differentiation is implemented. So I can have a look which library it was, and probably there is some connection between the ideas.
Yeah. It's interesting. So it's happy that I can learn something new for thinking.
Yeah, but this might be nicer. It's simple compared to this.
You had also a question?
Yeah, I still don't get it. How is it possible that it doesn't depend on the size, this age? If I would choose really, really big age, it would still work.
I was also like surprised. But I think the
I
main
believe
trick
you,
is,
but how is how?
but I think the main trick is that these imaginary rules are so chosen because the high, so these terms, colored terms are zero, and it's made in the way that the Taylor series in fact finish at the second order term, and then there is nothing. It's identically zero, so there is no truncation. So these formula are exact. So the only problem is there a round of error, but there is no subtraction cancellation error because of the minus. So the only thing which remains is a round of error on the most basic level. So I think the thing is that there is no truncation.
So cool.
Yeah, I was also surprised.